Hello guys, so in this video we are going to talk about transformer. What is the transformer and origin of the transformer? Okay, so we are going to talk about everything like the architecture of the transformer and what is the encoder decoder. Okay, so first of all we need to know transformer. Okay, so before we talk about chatgpt, GPT or generative AI, we first need to understand one core architecture behind all of them. Okay, that architecture is called the transformer. Okay, so a, a transformer is a machine learning model designed to work with text. It is mainly used for tasks like translation, summarization, and questioning answering. Okay, and the transformer was introduced in 2017 in research paper that is called a attention is all you need by Vashwani and his team. Okay, the paper changed the direction of natural language processing completely. Okay, so before why transformer was needed, why we need a transformer. Okay, by transformer was needed. So before transformer model like RNN, LSTM were used. These older model read text one word at a time. Okay, RNN and LSTM, these are the older model, and these model read text one word at a time. Okay, so I'm going to show you I love programming in Python. Okay, so if this sentence is long, the model slowly forget the beginning while reading the end. Okay, like I'm going to pass I love programming in Python. Okay, then it will read first word, that is I, and after this it will read love, then programming, then I, sorry, then in, and then Python. So it read one word at a once. Okay, or if the sentence is too long, the model slowly forget the beginning while reading the end. Okay, model forget what is in the beginning. Okay, while it will read the end. The key idea of the transformer is attention. Okay, so core idea of the transformer is attention. Instead of reading word one by one, the transformer read all word at the same time, or you can say the transformer looks at all words at the same time. It does not like RNN or LSTM, they read but one by one. Okay, but with the help of transformer we can read all word at the same time. Okay, it decide which word are important and how strongly they are related to each other. This make the model faster, more accurate, and easier to scale. Okay, so like I'm going to say I love programming in Python. Okay, so it is like I'm going to pass as I import I love programming in Python. Okay, so when transformer sees this sentence I love programming in Python, okay, it does not read it sequentially. Okay, I love programming in Python. Okay, it is the sentence. When transformer sees this sentence, I love programming in Python, it does not read sequentially by transformer. Okay, so it look at the entire sentence at once. Transformer look at the entire sentence at the once using attention. The model learned that programming and Python are strongly connected. Using attention, model learned that programming and Python are strongly connected. Okay, so during translation, Python remain Python and love become M. Aime. It's mean by in French, love. Okay, so transformer is made of two main part. Okay, so if you are going to pass input in encoder, okay, then it will go to the decoder. So the encoder's job is to understand the input text. Okay, so here encoder's job is to understand the input text. Okay, input text understand by the encoder. And decoder's job is to generate the output text. Okay, so these are the two main part of the transformer, encoder and decoder. Encoder job to understand the input text and decoder job is to generate the output text. Okay, so both encoder and decoder are not simple single block. Okay, both encoder and decoder are not a single blocks. They are a stack of multiple identical layer. Okay, so they have multiple layers. In the original transformer, we have 6 encoder layer and 6 decoder layer. Okay, but the important idea is this: a same layer is repeated many times. This repetition help the model learn deeper patterns. Okay, so why transformer are special? Transformer are special because they solve major problem of older models. Okay, they process text in parallel. Okay, they handle long range relationship. They scale very well. Okay, that's why model like GPT and what exist. Okay, so I already said that the key transformer is attention based model. Okay, that look everything at once. Means like if you are going to pass sentence, then it will look everything at once, or it can read everything at once. Okay, so here you can see this is the input and it will go here in transformer in this box, and then it will give you output here. Okay, I'm going to pass here input is how are you. Okay, I'm going to pass this input here in transformer, then it will translate this how are you in the cosmos states. Okay, this is the Spanish word of how are you. Okay, so if you are going to use transformer for translation, then it will work like this. Okay, you are going to pass here in input what how are you. Okay, then we need to pass here in transformer, then it will give you output. Okay, cosmo state. Okay, so here we can understand encoder and decoder. So we can say transformer made of two part, that is encoder and decoder. Transformer made by two part, that is encoder and decoder. Encoder, this one, this box is used to understand the input. Okay, encoder job is to understand the input, what you have in a input text. Okay, and decoder job is to understand, I mean generate the output. What is the output. Okay, so decoder job is to generate the output text. Okay, so both encoder and decoder are not a single layer, or you can say single block. Okay, they are the stack of multiple layers. Encoder also have multiple layers, decoder also have multiple layers. Okay, so here you are going to pass how are you. Okay, that is input, pass here in a encoder. Okay, so encoder will understand the input text. Okay, what you have in a input, that is how are you. Okay, and decoder, after this encoder pass its output inside the decoder here. So output of encoder will become input to the decorator. Okay, so decorator generate the output text here, cosmo states. Okay, okay, how are you will translate in Spanish, that is cosmo states. Cosmo states also how are you in Spanish. Okay, so that is our output, and this is the block, whole block, this orange, this line is called the transformer. And transformer is a combination of encoder and decoder. This one encoder and this is decorator. Combine, if you are going to combine both of them, then it will become transformer. So here you can see, I already said that we have encoders and decoders, okay, but we have in original architecture it consists 6 encoder or 6 decorator, okay, but we can replicate as many as we want. Okay, so let's assume n layers in encoder and n layers in decorators. Okay, so all encoder present the same structure. These encoder have same structure, and the input get each of them. Okay, how are you get from encoder 1, encoder 2, encoder 3, encoder n. Okay, so I'm saying input get into each of them, and it's passed to the next one. Okay, all all decorator present with same structure as well. These decorator also have same structure, and get the input from the last. Here you can see last encoder and the previous decorator. Okay, so here you can see encoder n, and its output will go here as an input in a decorator. Decorator 1, decorator 2, decorator 3, and up to decorator on. So here you can see I said that it will get input from the last encoder and the previous decorator. Okay, so these are the like I already have decorator 1. Okay, so if I am going to pass decorator 2, so it will go decorator 1's output will go here in decorator 2, and encoders out encoder I mean last encoder output also go here as an input in the decorator 2. Okay, similar we can pass in decorator 3 and decorator 4. Okay, so I mean output of n decorator, my last decorator, uh, we will pass here in every decorator as an input. Okay, and also pass the previous decorators out here. Okay, like if you are going to pass how are you as an input, it will go here encoder 1, encoder 2, encoder 3, encoder n. Okay, then we got here output in encoders. Okay, so this output will become input of decorators. Decorator 1, so we need to pass this in decorator 1, decorator 2, decorator 3, and decorator n. Okay, and here you can see we also pass previous output on the decorator. Okay, I hope you got it. And then we got our output como states. Okay, this is the Spanish word of how are you. I mean it's a Spanish word como states. Okay, this is the translation of how are you. Why is it special? I mean, why transformer is special? Okay, so we use transformer because they solve the problem faced by the older model like RNN and LSTM. Okay, so first point, that is parallelization. Okay, so before in older model we face the problem, RNN or LSTM don't use parallelization. Okay, so transformer process all word in a sentence at the same time, making them much faster to train. Okay, and second point, long range dependency. Transformer can capture the relationship between words even they are far apart in a sentence. This is difficult for RNN and LSTMs. Okay, and third point, attention mechanism. They use an attention mechanism that allow each word in a sentence to focus on other important words, improving understanding and context. Okay, and fourth point is scalability. Transformer can be easily scaled, making them suitable for large model like GPT, BERT, and many more. Now we will understand how attention actually work by using real examples. Okay, let's take one simple sentence. For example, I love programming in Python. Okay, when human read this sentence, I love programming in Python. Okay, so we will automatically understand the relationship between these words. Okay, but machine does not understand the language like human do. Now we are going to move here what attention does. Okay, self attention help the model answer very basic question. Okay, basic question like who is speaking. So I took this example previously. I love programming in Python. Okay, so I is the speaker. Okay, who is speaking? I stand for speaker here. Okay, and what is the action? Love. Love is the action. Okay, and what is the activity? Programming is the main activity. Okay, and what is the tool? So Python is the tool. Okay, who is speaking? I is the speaker. What is the action? Love. Love is the action. What is the activity? Programming is the activity. Okay, and what is the tool? Python is the tool. I use this example. Okay, so self attention help the model answer very basic questions. Okay, and attention help model connect these relationship mathematically. Attention assign importance score between the words. Attention assign importance score between the words. Okay, so each word look at other words and decide how important they are for understanding the meaning. Okay, this importance is stored as an attention score. For example, here, okay, so this is the example translation example. Okay, English to French. So here you can see I love programming in Python. Okay, and I'm going to translate this into this GM programming in Python. GEM programmer in Python. Okay, so during the translation, model learn that Python should remain the same. Okay, during the translation, model learn that Python should remain the same. I it also learned that I love this line. I love first word I love should become gem. Okay, here you can see I love should become gem. Okay, and this happened because attention highlights which word matter together. Now we are going to talk about what we have inside the transformer. Okay, so this is the basic flow. Okay, first of all I need to take one text as an input, then we need to do tokens. We need to convert text into a tokens, and after that we need to do it is embedding. Okay, after embedding we do need to do positional embedding. Okay, after this attention and connect with the encoder, decoder and output. Okay, so this is the entire transformer pipeline. Okay, text goes in and output comes out. Okay, so everything in between is just a mathematical processing. Okay, so here you can see this is our another diagram. Okay, this is in horizontal, or you can write like this in vertical: text, tokens, embedding, self attention, encoder, decoder and output. Okay, so first of all I need to take text. Okay, that is I love programming in Python. Okay, this is the text. Okay, and after this I need to do tokens. I need to do tokenization. Okay, I need to convert text into a tokens. Okay, so what is the tokens? Okay, so first stage is the tokenization. Okay, so the sentence is broke. This sentence is going to break into a smaller piece. Okay, that is called a tokens. Okay, here you can see this sentence broke into a smaller piece called the tokenization. Okay, here you can see I comma love comma programming comma in comma Python. Okay, so this sentence broke broken into smaller piece, that is called the tokenization. Okay, so this is first step, we need to do tokenization. Okay, and after this we need to do embedding. Okay, after tokenization, here you can see, after tokenization we need to do embedding. Okay, so here in embedding, what I'm going to do, in embedding, each token is converted into a numeric number. Each token is converted into a numbers. Okay, here you can see I convert into a 0.21 comma 0.88 comma 0.03. Okay, similar, we need to convert love in vectors. Okay, and Python also convert into a different vectors. Okay, so here you can see each token is converted into a numeric form, that is called the vectors. Okay, and these processes are called the embedding. These number are called the embeddings. Okay, the model never sees the word, it only sees the number. Okay, meaning is stored the mathematically. Okay, so this is called the embedding, and this is the tokenization. Each word is stored in a, each sentence is broken into a smaller piece, it is called the tokens. Okay, I already said that model cannot read the sentence, it only understand the tokens. Okay, here similar, I'm going to say embedding. Okay, embedding is just a number, or you can say we need to convert text into a numeric format, that is vector, that is called the embedding. Okay, or you can say, model never sees the word, they only sees the number. Okay, after this I'm going to move here positional encoding. Okay, so what does it mean? Transformer read all the word at the same time. Okay, here you can see, oh, no, here you can see transformer read all the word same time. Here transformer read all the words at the same time, so they need help understanding the word order. Okay, transformer read the word at the same time, so they need help understanding the word order. Okay, positional encoding tell the model which word come first, second, and so on. Okay, so here we can see positional encoding means we give position for I at the position of 1. Okay, and love at the position 2. Okay, and programming, what is the position of the programming? 3. And position of in, that is 4. And position of Python, that is 5. Okay, that transformer read all the word at the same time. Okay, so they they understand the word order. Okay, so positional encoding means transformer understand the order of the word. Okay, and after positional encoding we move here self attention. Okay, so here you can see in self attention means here in this self attention means bird look at other birds. Okay, self attention means bird look at other birds. Okay, the word love, here you can see love focus more on programming. Here love focus more on programming. Okay, and programming, here you can see love more focus on programming and Python. Okay, this is how context is built. Okay, this is not a understanding, this is the baited math. Okay, now we move here encoder and decoder. Love. Okay, so here after self attention we move here in encoder and decoder. Okay, so I already show you diagram, but here I'm just going to explain again. Encoder understand the input and decoder generate the output. Encoder understand the sentence and decoder generate the translation. Okay, together they form the transformer, these two. Okay, encoder and decoder. Okay guys, and after this, here after this I got our output here. Okay, so this is the basic pipeline, or you can say pipeline or architecture of transformer inside the what we have inside the transformer. Okay, so this is the pipeline of transformer. Okay, text. First of all, you need to take one text and need to do tokenization and need to do embedding. After embedding, you need to do positional encoding. Okay, after this we need to do self attention. Okay, after this we have encoder, decoders, and finally we got our output. Okay, so this is the basic pipelines of transformer: text, token, embedding, positional encoding, attention, and encoder, decoder, and output. Okay, first of all you need to take one text, and then you need to do tokenization. After tokenization you need to do embedding are converted text into a numeric format, that is vectors. Okay, that is called the embedding. Positional encoder. Okay, so after this we need to do attention, self attention, and after this we have encoder and decoder. Okay, now we can see real life benefits. Okay, fast training process every, I mean transformer process everything in parallel. Okay, so training should be fast. Okay, fast training, and it will give you better accuracy, scale to large models. Okay, so that's why they are faster, and that's why model like gpt exist. Okay, so gpt use transformer, better training, better accuracy, scale to large models. I hope you got it. Now we are going to talk about real application of transformer, or you can say transformer in real life. Okay, so this is why transformer are everywhere today. Chatbot like ChatGPT use transformer. Okay, chatbot like ChatGPT use transformer to understand and generate response. Okay, they are also use summarize. Okay, they are also use summarize long documents, and even to generate captioning for images. Now we can see here myth break. Attention is not equals to understanding. Then what is the attention? If it is not understanding, then what? What attention really is? Attention is just a weighted math. Okay, it calculates similarity score between the tokens. Okay, the model does not think, it does not understand meaning. It does not understand meaning. It only learn pattern from large amount of data. This is why hallucination happen. The model may sound confident but still produce incorrect answer. Attention cannot verify truth. It only predict what look like. It only predict what looks like. Transformer is not equals to reasoning engine. Okay, first point is pattern matching. Transformer are excellent pattern matcher. Okay, second point is not logic, means they do not perform logic. Okay, and third point is not critical thinking. They do not do critical thinking. Always remember this when using GPT like models. Now we are going to understand transformer encoder architecture step by step. Okay, so in this video we will focus on the transformer encoder. We will break down its architecture and understand each component step by step. I already said that a transformer has two main parts. First is encoder and second is decorator. Encoder's job is to understand the input text and the decorator's job is to generate the output text. In this video, we will focus only on the encoder. Okay, so encoder is not a single block, it is the stack of multiple identical layers. Each layer has the same structure and parameter but process the data sequentially. The original transformer used 6 encoder layers, but in practical we can use more or fewer. Okay, so now you can see here this is the diagram for transformer. Okay, I already said that uh, encoder has 6 layers, but we can use many. I mean many more or fewer. Okay, so I just took here n. Okay, for encoder 1, encoder 2, encoder 3, and encoder n up to n. Okay, so these all encoder has same structure, and these are the, like, we will talk later about decorator. Okay, now in this video we are going to talk about encoder only. Okay, I already show you architecture of sorry, pipeline of transformer. Okay, so you can see here encoder input flow. Okay, this is the encoder input flow. I can write here encoder input flow. Okay, so this is the encoder input flow. Okay, text tokens embedding in positional encoding and encoder. So before entering the encoder, text is tokenized. Okay, I already show you how can we tokenize the sentence. Okay, each token is converted into a embedding. Okay, and then we need to add position. You can say positional encoding is added, so the model know the word order. Okay, this combine the representation is the input to the encoder. Okay, so this is the encoder input flow. First of all, you need to take one sentence and then you need to do tokenize. You need to perform tokenization, and after this you need to do embedding and add positional encoding, and it will pass to the encoder. Okay, so this is the encoder input flow. Okay, so you can see here each encoder layer consists 5 main component. Okay, these are the 5 main component. Okay, first of all, first one is self attention, second is multi-head attention, third is feed forward neural network, and fourth is residual connection, and fifth is layer normalization. Okay, so these are the encoder layer components. Okay, we already saw how data flow through the transformer. Now we will zoom into just one part, the transformer encoder. Okay, so now we are going to understand this part. This is the this part is for transformer encoder. Okay, so we are going to understand this part. Don't worry about this part. Okay, right part, don't worry about this right part. Today we only care about the encoder block. Okay, encoder block on the left, this one. So here you can see encoded input, encoder input. Okay, this is the first part. Okay, here you can see input embedding and source sentence. Okay, so encoder takes word embedding as an input. Like if you have any sentence, okay, i I love programming. I mean, you can say anything. Okay, I love programming language, that is Python. Okay, so you can take any sentence, okay, as an input. Okay, So here you can see the encoder takes word embedding as the input. Okay, so if you have sentence, then you have you need to do tokenize, and after tokenize you need to do embedding. After embedding you need to add the positional encoding, that it will maintain the order of the word. Okay, so here encoder takes word embedding as the input here. Okay, since transformer process all the token at once, they need positional information. So we need add here. So we need to add positional encoding to embedding to tell the model the order of the word. Okay, it will tell the model that what is the order of the word. Okay, so this combine the representation goes into the encoder stack. Now we move here in self attention. Okay, here in this walk. Okay, so I already said that every encoder has these 4 or 5 layers. Okay, multi-head attention, add and normalization, feed forward. Okay, add normalization and residuals. Okay, these 5 layers we have in every encoders. Okay, so self attention, here you can see self attention allow each word to look at other word in the same sentence. For example, in the sentence I love programming in Python. Okay, so programming may pay more attention here. Programming may pay more attention to the Python. This help the model to capture the context and relationship, not just word position. Okay, so this will help the model to capture context and relationship, not just the word and position, not just the word position. Okay, and so here you can see instead of using attention, we use multi-head attention. Okay, so instead of doing attention once, transformer use multiple attention heads. Each head learn a different type of relationship. Okay, one head may focus on grammar, another on meaning, and another on long distance dependency. All head are combined together. That's why it is called the multi-head attention. Okay, so after attention, here we apply add and normalization. You can say add and normalize. So add means we add the original input back using a residual connection. Okay, so this is the residual connection. We use residual connection here. Okay, so we are going to, add means we add the original input back using a residual connection. Okay, so here we are going to add original input back, okay, by using residual connection. This connection is called the residual connection. Okay, so normalize help stabilize training and keeps value in a good range. This makes deep network easier to train. Now after add and normalization, okay, next come to the feed forward neural network. Okay, this is the simple neural network here applied independently to the each token. It helps transform the representation learned by the attention into a richer form. Okay, same network, same weight applied to every tokens. So here after feed forward, we move here add and normalization. Okay, after the feed forward network, we again apply the add and normalize. Okay, so this complete one encoder layer. Okay, now we can say, or what you say, the output of one encoder. Okay, this is one encoder. Okay, so the output of one encoder layer become the input to the next encoder layer. Okay, after passing through all encoder layer, we get context aware representation of the input sentence. This representation is later used by the encoder to generate the output. Okay, I already show you. Okay, we have multiple layers. Okay, 1 2 3 4, these are the encoders layer one by one, and they follow same structure. Okay, I already said that. Okay, this thing. So output of the one encoder layer become the input to the next encoder layer. Okay, after passing through all encoder layer, we get a context aware representation of the input sentence. Okay, so here this is this diagram for one encoder. Okay, first of all you need to pass like embedding of your sentence and then add to the positional adding, positional encoding, and after this you need to do like multi-head attention and use add and normalization, and after this we need to pass everything here in feed forward neural network, and after this we need to add and normalize. Okay, this is for one encoder, this is step for one encoder. And here you can see, we will understand this after some time. Okay, this is the decorator part. So now we are here in encoder. So encoder job is not to generate the text. Its job is to understand the input sentence by building rich contextual representation. Generation happen in the decorator and understanding happens in the encoder. Understanding happen in the encoder in this part, and generation happen in the decoder in this part. Okay. Okay, so I'm going to explain again in like a story. Okay, so word are converted into a number. Okay, with embedding and positional information here. Then self attention lets each word look at all other word to understand the context. Okay, so finally simple neural network. Okay, here simple neural network refine the information layer by layer to deeply understand the sentence. Okay, and if you like, you can say embed, attend. Okay, first stage is embed here, attend here, refine here, and repeat. Okay, embed, attend, refine, and repeat. Now we are going to understand self attention deep but intuitive. Okay, in the end you should say, oh, attention just a relationship between the words. Okay, and in this video we are going to understand most important idea in transformer, self attention. If you understand this, everything else become easier. Why attention exists? So let's start with a simple question. I love programming in Python. When the model read this sentence, this one, okay, when model read this sentence, how does it know which word are related? For example, programming is clearly related to the Python, but not very related to the word I. Okay. For example, programming, this word is related. It's clearly related to the Python. Okay, because Python is programming language. Okay. So programming is related to the Python. Okay, but not very related to the word I. Okay, so older model read word one by one and try to remember everything. That was slow and unreliable. Attention was created so every word can directly look at at every other word. Attention was created so every word can directly look at every other word. Okay. In one word looking at other words. In self attention, each word asks a simple question: which other word matter to me? Okay, the word programming, this word, the word programming looks at the all other words. Okay, but it pay more attention to Python. Okay, this word programming looks at all other words. but I pay more attention to the Python. Okay, this is not understanding, this is just assigning importance. Okay, so here one word looking at other words and ask a simple question: which other word is matter to me? Okay, so now we are going to move here in QKV. Okay, so you might hear state term like query, key, and value. Okay, so query is what a word is looking for. What is the query? Query is what a word is looking for. Key. Key is what other word offer. This one. Key. Key is what other word offer. And value. Value is the actual information that get passed forward. A bird compare its query with the key. Okay. A bird compare its query with the key of other word and decide who deserve more attention. Okay, I'm going to repeat again. A word compare its query with the key of other word and decide who deserve more attention. You can see here. Okay, attention score. So result of this comparison. Okay, programming compare with Python and it related high. Okay, and programming relate to the love, that is medium. Okay, and programming relate to the I, that is low. Okay, so this result of the result of this comparison is called the attention score. Okay, high number means more focus. Okay, and lower number means less focus. This one, high means more focus and lower means less focus. So there is a no meaning here, only weighted relationships. Okay, he I mean, why attention is parallel? Here is something powerful. All words compute attention at the same time. The model does not wait for one word to finish before moving to the next. This is why transformers are fast and scalable. Self attention inside the encoder. This one here you can see I already explained this encoder diagram. Okay, so here you can see inside the encoder, this is the encoder part. Okay, inside the encoder, self attention, this one, multi head attention, self attention. Okay, this is the first major operations. Each word become context aware here. Okay, while looking at the other words. After attention, the word presentation is richer because it now include the context. Attention is not equals to understanding. Now an important part, now an important clarification. Okay, attention is not understanding. The model does not know what Python is. It only know that in many texts, programming and Python appears together. Okay, why hallucination happen? Confident output is not equals to current output because attention is just a math. The model can produce confident but wrong answer. It cannot verify facts. It predict what look aesthetically likely, not what is true. Now you can see this is the summary of our all these previous lecture summary. Okay, summary of all our previous lectures. Okay, so self attention allow word to look at other word. Okay, word to look at other word. It assign importance using numbers. Okay, attention is equals to weighted math means it assign the importance using number. Okay, parallel and fast, it run in parallel, that's why it is working fast. Okay, no real understanding means it does not think or reason. Now we are going to understand multi-head attention deeply. Okay, so in the last video we understood self attention. Okay, Now the question is, if attention already works, why do we need multi-head attention? This one. Okay, I already show you this diagram why we need for multi-head attention. Okay, so here we are going to understand why we need. Okay, so in self attention block, okay, self attention lets each word look at all other words. It calculates which word matter more for context, but there is a limitation. Okay, limitation of attention. Okay, here the limitation of one attention head. So one attention head can focus on only one type of relationship at a time. Okay, language is a complex. Words are related in many different ways. So in the sentence, I love programming. Here I'm going to write I love programming in Python. Okay, so this is in this sentence, I love programming in Python. One relationship is subject to verb. One relationship is subject to the verb. Another is activity to tool. One head cannot capture all of this well. What is multi-head attention? Okay, so in this diagram, this is multi-head attention. Okay, multi-head attention means we run attention multiple time in parallel. Here we run attention multiple time in parallel. Head each head has its own view of the sentence. Same input, different focus. Think of each attention head as a different lens. Okay, here one head may focus on grammar, another head focus on meaning, another may focus on long range dependency. None of them is smarter, they are just different. Head are not independent thinker. Okay, so here attention heads are not mini brains. They don't reason, they don't vote, they don't debate. They just compute different attention patterns. Okay, and after this, how head are combined? How head are combined? Each head produce an output. Okay, here I have multi head attention. Okay, so we have different. I mean multiple head attention here. Okay, so here each head produce an output. These output are concatenated. Concatenated means joined together, not averaged. Then a linear layer mix them. More head is not equals to more intelligence. More head do not make the model intelligence. Okay, these head, this one. So more head is not equals to more intelligence. Okay, more head do not make the model intelligent. They only increase representational capacity. Too many heads can even waste the compute. Okay, so balance matter. And after this, why multi-head attention matter in practical, or you can say matter in practice. Okay, so multi-head attention helps models understand complex language patterns. This is why transformer work well for translation, summarization and chat. It improves the flexibility, not reasoning. So that's why we need multi-head attention. Self attention tell the model what to look at. Okay, self attention tell the model what to look at, and multi-head attention here tells the model how many way it can look. Okay, multi-head attention tell the model how many way it look, and self attention tell the model what to look at. Now we are going to understand feed forward network and positional encoding and stability layers. So in the end of video, you will say, oh, attention is not the only thing. These layer make transformer stable and powerful. Okay, so far we have talked a lot about attention, but attention alone is not enough. In this video, we will understand the other critical part that make transformer actually work. Okay, I'm going to explain again. In this video, we will understand the other critical part that make transformer actually work. Okay. Now we are going to cover these points inside the transformer encoder, feed-forward neural network, positional encoder, and stability. Where we are in the architecture feed-forward neural network and what is the feed-forward neural network actually does. Okay, so this is our diagram for feed-forward neural network. Okay, so we have multiple blocks. Okay, so this one is multi-head attention, this is for add and normalization, this is for feed forward neural network and positional encoder and add and normalization. Okay, so here an encoder block is repeated many times. Okay, this block repeated many times, each block has attention, this attention. Okay, but also has three very important components. These are feed forward neural network, this one positional encoding, okay, and add and normalization, this one positional encoding, sorry, this one. Okay, so here after multi-head attention, or you can say after attention, we have three more important component, that is feed forward neural network, okay, and positional encoding and add and normalization. Okay, so after attention, every word here after attention, like if you are going to pass embedding of a sentence here, and and after attention here, okay, every word goes through a feed forward neural network from here to here and here in feed forward neural network. This work independently on each word but do not talk to each other here. Okay, so attendance sorry attention this attention decide what information a word should look at. The feed forward neural network decide how to transform that information. Okay, attention help the word hi, hello, hi. So attention help the word hi understand its context from the AI. The feed forward neural network then refine this understanding here. Now we can see here feed forward neural network. Okay, so I think you already knew about feed forward neural network. In deep learning, you already studied that. What is the feed forward neural network? Okay, so the feed forward neural network, this one has two linear layers with a ReLU activation in between. Okay, so this is the feed forward neural network: input layer, hidden layers, and output layers. Okay, for example, this is the internal structure of the feed forward neural network. Okay, it has linear layer with ReLU activation function. Okay, so this is the input layer, these are the input x1, x2, x3, and these are the weight w1, w2, w3. This is the weight for x1, this is the weight for w2, that is for input x2. Okay, this is the input xm and its weight of x wm. Okay, so these are the weight, and here we are going to add all of these. Okay, x1, w1, x2, w2 here. Okay, this is wise, and here this is the activation function. Okay, so we can use ReLU or any of other sigmoid softmax according to your need. Okay, so here we have feed forward neural network. Okay, and it has two layers, or you can say two linear layers with a ReLU activation function. Okay, ReLU activation function in between. Okay, so this is the activation function and this is the output. Okay, so some transformer is applied to every word. This increase the representation power of the model. Okay, so here this is the structure of feed forward neural network. Okay, the feed, I'm going to explain again. The feed forward neural network has two linear layers. Okay, input layer, output layer, and it has ReLU activation function in between. Okay, so transformer is applied to every word. So same transformation is applied to every word. This increase the representation power of the model. Okay, this one transformer. inside the transformer we have feed forward neural network, this one, okay. And this is the internal architecture of feed forward neural network, okay. So here I say that this feed forward neural network has two linear layers with ReLU activation function, okay. And and same transformation is applied to everywhere. This increase the representation power of the model. By feed forward neural network is position wise, okay. So each word is processed separately here. Each word processed separately, like high does not influence AI here, okay. So for example, I have this word high, so this high does not influence with the AI here, okay. So this makes computational computation efficient and easy to parallelize, okay. So that's why we need feed forward neural network is positional wise, okay, because high does not influence AI here, okay. So why we, so here you can see uh, feed forward neural network we add here positional wise, okay. So we need to add position here, positional wise, okay. And after this positional encoding, okay. So here positional encoding transformer read all the word at the same time, okay. So transformer read all the word at the same time, so they have no natural sense of order. So without positional encoding word order would be lost, okay. So you can see here what positional encoding does, okay. So positional encoding add position information to word embedding, okay. For example, high at the position 1 and high at the position 5, so will have, okay, will have different embedding, okay. So we have a different embeddings for at position 1 and for at position 5. High at position 5 has different embedding and high at position 1 also have different embedding, okay. So that's why we add positional encoding add the positional information to word embedding, okay. It is going to add the positional information to the word embedding, okay. So that's why we need to add positional encoding, okay. So this is how the model know which word come first. Now we are going to move on this point how positional encoding is created, okay. So you look at here positional encoding, okay. So positional encoding are created using sine and cosine function, okay. This create a smooth and unique pattern for different position, this one, okay. Here, so with the help of sine and cosine we can add, I mean we can say positional encoding are create using cosine and sine function, okay. So this create a smooth and unique pattern for different position, okay. Now we can see add and normalization, okay. This one, add and normalization, this one, add and normalization. So now come a very important concept, stability. Deep model are hard to train, okay. So add and normalize layer help to model train properly, okay. So this layer help the model to train properly, this one, okay. And after this we can see here residual connection, okay. So this is our, in red line I have residual connection, okay. So residual connection means we add the input back to the output, okay. So this is our input, I'm going to add this input back to the output so the model doesn't forget the original information, okay. Okay, in RNN and LSTM we forget the input, okay. But with the help of residual connection we can remember, okay, what we have in our input. So residual connection means we add the input back to the output so the model doesn't forget the original information. This help the prevent vanishing gradient, okay. It's like keeping a shortcut in the network. Okay, so in you can say in one line, it is like keeping a shortcut in the network. Okay, and after this we can see here fourth point, that is layer normalization. Okay, layer normalization, I already add layer normalization, sorry, layer normalization. Okay, so layer normalization make value more stable. It ensures consistent scale across the layer. This leads to faster and more stable training. Let's summarize the encoder block again. Okay, this is like I'm going to provide you some summary. Okay, so here you can see this is input. Okay, so input embedding plus positional encoding. Okay, after this we need to do, I mean we need to pass here in multi-head attention. Okay, and here I'm going to add and normalize this layer. Okay, and after this it will pass here in feed forward neural network and add and normalize again. Okay, this entire block is repeated multiple times. Okay, so this is the complete encoder block. Okay, so by this method attention give you context. Okay, feed forward network at the depth, this one attention will give you context, and feed forward neural network add depth. Okay, positional encoding add orders, this one positional encoding at the orders, and residual connection, these are the residual connection in red. So residual connection and normalization at the stability. Okay, together they make transformer scalable. Okay, so here finally we say attention find the relationship ffn, sorry, fnn means feed forward neural network, refine them and add and normalize. Okay, and keep things stable. Okay, so I add extra z here, I need to remove this is keep. Okay, attention find the relationship f and n, refine them, add and normalize these, add and normalize, keep things stable. I hope you got it. Now we are going to move on decorator in next section. I already finished encoder part of transformer. Now we are going to understand transformer decorator, how text is generated. In the end of video you should say, okay, now I understand how GPT actually generate text one word at a time. Okay, you will understand, okay, how GPT actually generate text one word at a time. So the transformer decorator from understanding to generation. So for we have seen how the encoder understand the input. Okay, so now let's talk about the decorator. So decorator is the part that actually generate the text. Now we are going to understand encoder versus decoder. Okay, so here this is the diagram for encoder. This part is for encoder. Okay, and this part is for decorator, and this is the whole architecture is for what? This is a transformer architecture. Okay, first part is encoder and second part is for decorator. So encoder, here you can see here this part I already explained multiple times. So encoder read and understand the entire input sentence. Okay, and decorator, this part generate the output sentence. Okay, so it does this one word at a time. So this is how translation and text generation happen. Okay, so after this we move here why the decorator is different from the encoder. Okay, so why this part is different from this part. Okay, so here the decorator is different from the encoder in one key way. Okay, it must not see future words, it must not see future words. If it could, it would be cheating. Okay, so yes, use the word cheating, human get it instantly. Okay, now we are going to move here, mask multi-head attention. Okay, so here in decorator you can see mask multi-head attention, this one. Okay, this is called the mask self attention. Okay, mask multi-head attention or mask self attention. Masking means blocking future word, it will block the future words. Okay, the model is only allowed to look at past and current token. Here model is only allowed to look at past and current token. Okay, and by masking is necessary. Okay, so text generation is auto regressive. Okay, so that means the next word is predicted using only previous word. If the model could see the future, it would already know the answer. That would break the learning completely. Okay, so that's why we use masking, or masking is necessary. Okay, for example, I have hi AI. Okay, so let's take simple example, that is hi AI. Okay, at step 1 the model only see hi, this one. Okay, it predict the next word. Okay, at the step 1 model only see hi. Okay, it predict the next word. At the step 2 it see hi AI. First it, I mean at the step 2 it sees hi and AI. So, but nothing beyond that. The mask insert this behavior. Okay, I'm going to explain again with this example. At step 1 the model only see hi. Okay, it predict the next word. At step 2 it sees hi AI. Okay, but nothing beyond that. The mask insert this behavior. Internally this is done using the casual mask. Okay, it block attention to the future positions. You don't need to remember the matrix, just remember the rule, no picking into the future. Now we are going to understand encoder and decoder attention. Okay, so this is the part. Okay, encoder and decorator attention. Okay, so because encoder, okay, so here you can see output of the encoder is connected here, and output of this layer, or you can say this is the decorator attention. Okay, so decorator attention and encoder attention. Here this is the encoder attention and this is the decorator attention, this line. So it is called the encoder decoder attention. Okay, so I'm going to show you one another diagram. Okay, so here this is, you can say this is the encoder attention because it is the encoder, and this is the decorator self attention. Okay, and here you can see this one, decorator encoder attention. Here this one, because encoder is connected here and also decorator is connected here, so this is called the encoder decoder attention. Okay, this part. So now come encoder decoder attention here. Okay, so this is where the decorator looks at the encoder output. Okay, so here you can see decorator look at the encoder's output. This allow the decorator to use information from the input sentence, this one. Okay, so why encoder decoder attention matter? Okay, so here decoder has two source of information. Okay, this part has two source of information. First, what it has generated so far, and second, what the encoder understood from the input. Okay, encoder decoder attention connect these two. Okay, now we can see here how it works. Okay, so decorator ask the questions. It asks which part of the input sentence should I focus on right now. Okay, decorator ask the question which part of the input sentence should I focus on right now. The encoder provide the answer. So here by the encoder, it provide the answer by the encoder. Okay, so encoder provide the answer. Okay, so here after this, translator analogy. Okay, so think of a human translator. Okay, think of human translator. So they read the full sentence first. Okay, and then they translate word by word. At each step they look back at the original sentence. That's exactly what the encoder does. Okay, here now we are going to understand feed forward neural network in decorator. After finishing these, okay, we are going to understand feed forward neural network in decorator. Before we understood uh, encoder decoder attention matters. Okay, and here feed forward neural network in decorator. We are going to talk about this feed forward network in decorator. Okay, so this one. After this we are going to move here feed forward, okay, network, or here you can see this one feed forward network. After taking transformer from the other token, okay, so we will understand this later. Okay, so here we are going to understood. I'm going to explain this. Okay, so here just like the encoder, okay, just like the encoder, decoder also has feed forward network. Okay, you can see here encoder has feed forward network and decoder also has feed forward network. It refines the information at each position. Again, this happen independently for each words. Okay, and after this we have final layers, final linear and softmax layer, this one linear and softmax. Okay, after all the attention and processing, the decorator output vectors. Okay, so these vectors are not worded. The linear layer map them to vocabulary size. So softmax convert this into a probability. Okay, so here I'm going to explain again. Okay, after all the attention and processing, the decorator output vectors. These vectors are not worded. The linear layer maps them to vocabulary size. Software convert this into a probabilities. Okay, so here after this predicting the next word. Okay, so each probability represents how likely a word is to be a next. The model select one word and move to the next step. This process repeat until the sentence is completed. Okay, so why this is powerful? This design allow the model to generate the text. It works for translation, chat, summarization, and many more. This is the core of GPT like models. Okay, so now I'm going to explain summary of decorator. Marks attention, prevent the cheating. This mask attention are used to prevent the cheating. Encoder, decoder, this one. This is used for prevent the cheating. And this part, encoder, decoder attention, bring the context and feed forward neural network refine the representations. Okay, linear and softmax convert vector into words. These two are used to convert the vector into the words. Okay, so this is the basic summary of decorator. First, this layer mask attention prevent the cheating. Second layer, this is encoder decorator attention bring the context. Okay, and here feed forward network refine the representation, and linear and softmax convert the vector into the words. So far, we have learned how transformer work internally. Okay, now the big question is why do different transformer model exist? And why do bigger model feel more powerful? So this video will answer both. Okay, so here you can see type of transformer model. Okay, not all transformer are the same. First type encoder only transformer. What is the encoder only transformer? I will explain later. Okay, so this part is for only encoder, this one. Okay, and second type decorator only transformer. This part is for decorator only transformer, this one. Okay, and third part is, third type is encoder decoder transformer. means it include both encoder and decoder. Okay, so here we are going to understand these in this video. Okay, so first type of transformer, encoder only transformer. Second type, decoder only transformer. Third type, encoder decoder transformer. Okay, so these are the three types of transformer models. Okay, I already said that all transformer are not the same. Okay, so the difference come from how the encoder and decoder are used. Okay, based on this transformer fall into three categories. Okay, I already said that these are the three categories: 1, 2 and 3. Okay, so encoder only transformer, we are here, this one, encoder only transformer. So first, encoder only transformer, these model use only the encoder part. Their job is to understand text, not generated it. Okay, so this one. Okay, so first this part. Okay, this is the first part, encoder only transformer. Okay, so this is for encoder only transformer. These model use only the encoder part, and their job is to understand the text, not generated it. Okay, so here what encoder only model are good at. Okay, so they are excellent at tasks like text classification, semantic search and embedding. Okay, they process the entire input at once and produce the rich contextual representations. Okay, encoder only examples: word, ro, word a and distal word. Okay, so these are the example of encoder only transformer. Okay, so these model read very well, but they don't write long text. Okay, these model read very well, but they don't write the long text. Okay, and they use this part of transformer, that is called the encoder only. Okay, so after this we are going to move here, decoder only transformer. Okay, so second part, decoder only transformer. This is the second part, decoder only transformer. These model. Okay, so these model, they use only decoder only transformer. Okay, so these model use only the decoder with mask self attention. This one, mask self attention in encoder and encoder decoder part. Okay, so these model use only the decorator with mask self attention. Their straight is text generation. Sorry, their strength is text generation. Okay, so they will generate the text. So here you can see what decorator only model do. Okay, so they generate text one token at a time. Each new token depend only on previous generated tokens. This makes them perfect for GenAI. Okay, and here you can see popular example of decorator only: GPT-2, GPT-3, GPT-4, LLaMA and Mistral. ChatGPT is a decorator only transformer. Okay, and here we can see encoder decoder transformer. So here this is the third part or third type, you can say, encoder decoder transformer. So they use both encoder this part and decorator this part. Okay, here these model use both the part. Okay, and they are best when one sequence must be transformed into the another. Okay, so here decorator, encoder decorator use case. Okay, so common tasks include translation and summarization. The encoder understand the input, this part will understand the input. Okay, the second decorator generate the output while attending to the encoder. Okay, and here encoder decoder example, that is T5 and BERT. Okay, and the original transformer from the 2017. Okay, but T5 and 2017, I we got in 2017 we got original transformer. Okay, and here I'm going to summarize again. Encoder only model are used for understand. This part is used for understand. Okay, and these model are BERT, row word, distal word. Okay, and decorator model are used for generation. This part are used for generation. This one. Okay, and model decorator only model GPT 3, GPT llama. Okay, so these are the model GPT 4, 2, 3, and Mistral. Okay, encoder decoder model are for a transformation. Okay, so encoder decoder I use both encoder and decoder. Okay, I hope you got it. So these are the type of transformer. First is encoder only, decoder only, second is decoder only, third is encoder decoder transformer. After type of transformer, now we are going to move here why scale works. Okay, why do bigger model feel smarter? Okay, why do bigger model feel smarter? Okay, so large language model feel more intelligent. Okay, but now because of magic they feel better because of scale, but not because of the magic. They feel better because of the skill. I'm going to explain again. Why do bigger model feel smarter? Large language model feel more intelligent, but not because of the magic. They feel better because of the scale. Okay, and here in this line you can see more layer is not equals to magic. Adding more layer does not automatically make the model smarter. Deeper model provide a more abstract representations. They compose pattern better, but depth alone is not enough. Okay, and here the three pillars of scale. Okay, so modern LLM improve because of three things. Okay, modern LLM improve because of three things. Okay, that is more parameters, more data, and more compute. All three must scale together. More parameter, more data, and more compute. All three must scale together. Okay, so what parameter, data, compute do? What parameter, data, compute do? Sorry, I did mistake while reading this. What parameter, data, compute do? So more parameter allow store more pattern, more data improve generalization, more compute improve the optimization. Scaling only work when these grow together. Okay, and here emergent behaviors. All all scale models so basic language ability. Okay, at large scale, new ability suddenly appears. This is called the emergent behavior. I am going to repeat again. At the small scale, model show basic language ability. Okay. At large scale, new ability suddenly appears. This is called the emergent behavior. Okay. Example of emergent ability. So these include reasoning step, code generation, few short learning, and instruction following. These ability are not explicitly programmed. Okay, and here next point is GPT-4 versus GPT-2. GPT-4 is not smarter because it understands like a human. Okay, it feels smarter because it is a larger. Okay, so GPT-4 is not a smarter because it understands like a human. It feels smarter because it is a larger, trained on more data and better alignment. Okay, so the core architecture is still the same transformer. Okay, now we can see final reality check. Transformer are powerful, but they do not truly understand meaning. Okay, transformer are powerful, but they do not truly understand meaning. They can hallucinate. Okay, they rely entirely on learn statistical pattern statistical patterns. Okay, and here final takeaway. Transformer work because of attention. They scale because of data, parameters, and compute, but they are still pattern learners, not thinkers. Transformer work because attention allow them to see the whole context at once. Okay, different transformer architecture exists because different tasks need different behavior. And large models feel powerful not because of the magic but because of the scale. At the same time, it's important to remember that transformers do not truly understand meaning. They learn pattern and sometimes they can hallucinate. Okay, so now we are going to move in another chapter. Okay, so now at this point I have finished transformer. I already explained everything. If you have any doubt, then you can go and watch my video, and you can watch a playlist I already uploaded in my YouTube channel, and that name is transformer. Okay, go and watch there. Bye bye guys. If you like my video, please do share, subscribe and comments.